good afternoon, everybody. Welcome to another edition of our Quantum Research Center seminar. Today, I have a very special pleasure. In the previous sessions, we've had speakers that I know personally very well, and today we have the pleasure of having Iordanis Kerenidis, whom I don't know personally too well. We've exchanged some emails in the past, and he was very, very kind to accept my invitation, even without knowing me personally. So I really, really thank you, Iordanis, for your time, for your availability. We understand how busy everybody is, especially when it comes to spending more time in Zoom. So Iordanis is a big authority in the field of quantum algorithms. He has a background in he's a computer scientist originally. He's been working in quantum algorithms for some time, and he has this, I was saying to him offline that he has this very nice feature of being able also to collaborate with experimentalists, which is non-trivial coming from computer scientists. Iordanis comes from a tradition of big names in quantum computer sciences. He did his PhD in Caltech, in University of California with Umesh Vasirani, who's one of the fathers of quantum computational complexity. Then he did a postdoc with Peter Shor in MIT. And then he moved to France as a CNRS research director, where he's been doing a great job. He's a European Research Council grantee. He's founder and director of the Paris Center for Quantum Computing. And he's been doing very world-leading research on quantum algorithms for machine learning and optimization, application for recommendation systems, demonstration of quantum classification task on trapped ion hardware, and also algorithms for Monte Carlo methods in finance, right? And by the way, he's also doing things in the private sector. So he's the head of quantum algorithms at QC Corp, right? Who I believe they are in Silicon Valley, right? Yes. Yeah. So this is a real great pleasure to have you here, Iordanis. Thank you very much again. And before I give you the word, remember, guys, that you can raise your hands, and if you want to interrupt him and ask questions, he gave me the okay, so we can do that too. You can either raise your hands, and I will give you the right to speech, so to say, or you can also, of course, go for the more conventional tool of writing typing your questions in the Q&A button, right? But do raise your hands if you have doubts during the talk. And yes, so now with this, I give you the word. Iordanis, proceed, and thank you again for being here, okay?
Thanks a lot, Leandro. Thanks for the invitation. I'm really happy to be here and give this talk. I hope it's the beginning of our collaboration, so I'm really looking forward to it. I will just start sharing my screen. Mm-hmm. Excellent. So in principle, you should be seeing my slides, right? So what I wanted to do today is discuss a little bit more generally quantum algorithms, but mostly look at these tools within the framework of quantum machine learning. So try to understand what are the prospects of quantum machine learning and what are the challenges, because there are many prospects, there are also many challenges, right? All right. So I guess the first question that is kind of interesting, and it becomes more and more interesting because, you know, you have seen all this investment that goes into quantum computing in all these centers and all the people who start working with quantum computing. The first question is, why should we care about quantum computing and why now, right? So we are kind of starting to understand that we are talking about a kind of a second quantum revolution. And I say a second because we have already had a quantum revolution coming from quantum mechanics, right? So all the work that people did in the beginning of the 20th century, there are many applications of this. For example, lasers or GPS or MRIs. So all of this type of thing, or atomic clocks. So these are applications and things that have came up because of our understanding of quantum mechanics and what quantum systems can do actually. And now we're going a step further and try to understand how can we encode information into these quantum systems and how can we compute with these quantum systems. And we are starting to see the first applications of what these quantum computers can actually do, right? So the first thing I think we all kind of know is that quantum computers are not just faster processors, right? So the idea is not that you will take your algorithm and your problem that you are already trying to solve in your classical computer, and you will just change the hardware at the back, and you will use a quantum computer and things will start working faster. So this is really not, unfortunately, as easy as that, because quantum is a fundamentally different way of performing computation, right? So it's based on some fundamentally different ways of encoding and computing with information. And the good news is that it can be much, much faster, but for certain tasks, right? Not for everything. There are many things where a classical computer can provably do as good as a quantum computer, right? But there are specific tasks where a quantum computer can do much better. And that sometimes it could be polynomially better or even exponentially better, okay? So this kind of implies that quantum computer is not going to replace classical computer, right? We will still have our classical laptops, right? But quantum computers, we expect them to open the way to new applications, and new applications in many different areas, whether this is about simulations within, climate studies or energy or finance, pharmaceuticals, drug discovery, healthcare, and all of this type of problems that are kind of very heavy, intensive computational problems that now we use like supercomputers and HPC machines and clusters of GPUs to solve, right? And for this type of problems, we really believe that quantum processing units, quantum computers, will be yet another type of hardware that we will be able to use, right? That will enable to kind of get rid of some of the bottlenecks that we have today for classical computers, okay? So what is clear here is that we need to really rethink and invent new algorithmic solutions. As I said, it's not the same algorithm that runs on your classical computer that we will just run in the quantum computer. We need to come up with new ways to take advantage of the power of quantum computers, okay? So this is what we have been trying to do, and I will show you a few examples of what do we know already, how to do, what are we hoping to do with these quantum computers, and where are we with respect to the hardware, and how far are we from really looking at real world applications, okay? Okay, so as I said, what we're trying to do is come up with these quantum applications, right? This first type of quantum applications, and we need two things to arrive to that point. The first thing is that we do need the hardware manufacturers to start building some better qubits and some more qubits. Okay, so right now we see the first quantum computers, right? Let me say the first quantum machines that can compute something, right? It's amazing, right? When I started working on quantum more than 20 years ago, if you would ask me, would we ever have a quantum machine with even 5 qubits or 20 qubits, I would say not in my lifetime. So the fact that we have arrived to that point, to me, it's amazing, right? But obviously we need better hardware. We need better hardware. But there is one other thing which we need a lot, which is to coming up with new ideas and new algorithms to manage to get to these applications where the algorithms will start needing less resources, like fewer number of qubits, and be able to deal with the fact that the qubits are pretty noisy right now, okay? So we need to have these two things happening at the same time to be able to get to these first quantum applications, okay? So my work is on the second side, is how to take advantage of quantum computers, and more precisely of these noisy intermediate scale quantum computers that we see happening today, or it will happen in the next 3 or 5 years, okay? And I will want to see and give you some examples of what we can do with these machines in the area of quantum machine learning, okay? So quantum machine learning, I always say that it's kind of the most overhyped and underestimated fields in quantum computing, right? It's overhyped because, it's already AI. We put quantum within AI, it becomes something that, media reports that the quantum computer brain will take over the world or something. So I don't think that this is what will actually happen. But at the same time, because machine learning, it's not an exact science, right? When it comes to computer science, that they want to prove everything mathematically and theoretically, there are many things that cannot be proved in machine learning. You really need to try them out in practice and see if it works or not, right? So there is there's both some sort of a lot of hope for what quantum machine learning can do. There are many statements which are a bit exaggerated. There are other statements which don't give enough credit to quantum machine learning. So what we're really trying to do is figure out where are we in this field and what are the real prospects for quantum machine learning. So here's the first very good thing that we have, right? Which is kind of a good starting point, because if this was not clear, then we wouldn't be here to talk about quantum machine learning. So this is the fact that we do have theoretical results that say that if we had big, large scale and fault tolerant quantum computers, then we can offer big advantages. Okay, so these are kind of many theoretical results, or we have, some of them come from my team, but there are many more results out there that show and prove and analyze how many, what kind of resources the quantum computer will need, meaning what will be the running time, for example, to solve a machine learning problem, whether this is classification or it is some unsupervised like clustering tasks, or some more general methods like interior point methods or gradient descent algorithms. So we have a lot of information that says that if we don't care for now that we have few qubits and noisy qubits, then we can in fact enhance what machine learning can do if we add this quantum capabilities to it. Okay. The second very interesting thing is that we don't necessarily have to wait 20 years or even more to have a perfect quantum computer, right? That may not even happen, right? The main question, and what was very interesting to me to understand, is that we also have kind of concrete ways of trying to bring these quantum algorithms that we know they exist out there for perfect quantum computers and bring them closer to reality. What do I mean by that? I mean that we have concrete ways of trying to figure out how to do these quantum machine learning applications with fewer qubits or with much more shallow circuits, meaning that we don't need to keep these qubits, coherent for a very long time. And these are some of the tools that we're going to use, and I will give you a little bit more details about them. For example, one of the bottlenecks was always, what do we do with all this classical data that we have, right? If we want the quantum computer to do something interesting, we need to somehow load this classical data. That could be images or they could be financial data. We need to be able to load this in an efficient way into the quantum computer, right? So you may have heard there were many ideas out there. There is this notion of QRAM, this quantum random access memory, but all of these were kind of futuristic ideas that we don't have the technology to build right now. The question was, can we use the same technology that we use to build quantum circuits and quantum computers to do this kind of very fundamental thing, which is load classical data to a quantum computer. So I will show you how to do this in a very efficient way. And once we do that, we can start doing some subroutines which are extremely important for machine learning. For example, one of the main things that you have to do in machine learning is that you have data points and you need to figure out if they're close to each other or far from each other. Right? If you want to cluster all the cats together and all the dogs together, you basically try to figure out if this is a cat and this image is very close to this, then it should be a cat, right? So there's this notion of distance between data points or similarity between data points, which is very important. And this is also something that we can see how quantum computers can do very efficiently, okay? And more generally, one of the main areas where quantum computers can be very good is anything that has to do with linear algebra. So what do I mean with linear algebra? I mean things like multiplying matrices together or inverting matrices, for example, when you want to solve a system of linear equations, or figuring out something about the eigenvectors and the eigenvalues of some matrices and things like that. And this is very important because if you really look at the core of machine learning, these are really the math that goes on. This is really what our algorithms do, whether it is for the more traditional machine learning, things like support vector machines or nearest neighbors or k-means clustering. So all these type of algorithms have to do with linear algebra. But also when we talk about neural networks and deep learning, there is, again, this is why we're using GPUs, because it is a lot about multiplying matrices and vectors and matrices together to do the training of these models, right? So these are some of the areas where quantum computing could be helpful. And now you can imagine the fact that there are many applications in machine learning, because most of machine learning is precisely based on these core mathematical procedures that have to do with linear algebra. Okay. And one last thing before I actually start giving you more details is that there are many different things that one may want in machine learning, right? So obviously we want to be fast and we want to be accurate, and this is great, right? But there are other things which are very important and becoming more and more important. For example, the interpretability of our models, right? When I discussed machine learning with sectors like healthcare or finance or pharmaceuticals, there's always a question that we cannot just train a neural network and have it take decisions for us, because there are very strict regulations, right, that say that if I make a decision, I have to be able to explain to someone why I made this decision, right? Because we are talking about patients, we are talking about people's invested money. So there are all these regulations that say you need to have this notion of interpretability, right? So one thing that quantum can also do is make all these more interpretable methods more efficient, right? And I will show you a few examples as well. There are also other notions like trust or energy savings. I will not really discuss them very much in this talk. Okay, so before going to the first example, any first comments or any questions? I just gave you a general introduction about the topic, but if there are any questions.
I think it's very clear. This is a great introduction, Iordanis. You can go ahead. There are no questions for the moment.
All right, perfect.
Thank you. This is going great. Thanks.
So what I wanted to start with is an example of where are we right now, right? What can quantum computers do right now about machine learning?
Oh, hold on. We have a question. We do have a question from Luigi.
Sure.
Hold on. Let me give him. How do I? 1 second. How do I make him? No, Luigi. 1 second. Luigi Nico. How do I make him? 100. 1 second. I don't see the button to make you.
I think.
Oh, thanks. Luigi, did you have a question? Sorry.
Yes.
Okay, shoot. Go ahead.
Hello, Iordanis. Basically,
Hi,
we shared many times, lot of time in Singapore, in CQT.
True.
Yeah. So I have a small. Actually, you made an interesting statement on the kind of problems you can tackle with quantum computers, because I thought that basically you can. So when you have a universal quantum computer, in principle, everything is expected to be faster if you compare with classical machines, right? But instead you are saying that there are some problems for which quantum computers may be not as efficient as classical, or at least you cannot prove that you have a supremacy. Can you please clarify on that?
Sure. So a classical computation is a subset of what a quantum computation can be, right? Because a quantum computer can also do classical computations, right? So this means that a quantum computer will not be worse than a classical computer, right? But for some problems, the optimal way of solving a problem is by doing some classical computation, which means that you're not going to gain anything by using a quantum computation, right? Because what you really need to run is a classical algorithm. So you might as well run it in the classical computer. Okay. So it is not true that you can speed up everything, right? There are specific problems where you can prove lower bounds that say that the number of gates or the number of time steps that the quantum computer will need is the same as the classical one, right? In which case you can use the classical one, right? There are other cases where we can prove that the quantum computer can provide an advantage, right? We can prove that, the best classical algorithm needs many more gates or time steps than a quantum computer, right? And then there is a big, set of problems where we know that these problems, for example, all the optimization type of problems, these are problems which we know that in the worst case, they're going to be hard both for classical computers and for quantum computers, right? And the question there is, what kind of heuristics can you come up with and how good are they going to be? So these heuristics are not going to work for everything, for every instance of the problem, but you only care for them to work at the instances that you really want to solve, right? So there, for example, it's still not very clear, right, for what type of instances the classical algorithms will be better and for what type of instances the quantum algorithms will be better, right?
This was basically my question.
Yes, yeah.
So whether you can characterize which one it's, so what problems you can solve with better with classical machine was better.
So you can characterize in some cases when you want to look at worst case guarantees, right? Saying, can I always solve this problem faster or not? Then you can characterize not everything, but some things, right? Because you can prove lower bounds and stuff. But when it comes to heuristics, like here is an optimization problem, find a good solution for me, right? There, neither the classical nor the quantum can guarantee a good solution for every instance, right? So there we have to test them on real instances and figure out if the classical is better or if the quantum is better, right? And I think you're right. At the end, what will happen is that for some cases, the quantum will be better. For some cases, it's not going to give you anything better than the classical computer.
Okay,
right.
Thank you.
Thank you, Luigi, for the question.
Okay, great question. Okay, so here is, as I said, the first example of what we can do right now. Okay, so we looked at kind of the most basic, let's say, problem in machine learning, which is classification. So we have different types of data. It could be financial data, it could be, medical images or signals that an autonomous vehicle gets from the environment. It could be users and preferences of users for products like in Netflix or in Amazon. So we have this type of data, right? And what we want is we want to perform some classification, right? We want to classify whether, the medical image is normal or we see that there is something wrong with it, right? We want to characterize if a product is good or bad for a user and so forth, right? So what we needed to do here is come up with some quantum algorithms to do classification, right? And I guess one simple way to do it is by looking at what do we do on the classical computer and try to figure out how to create quantum analogs of these algorithms, right? So kind of one of the simplest, algorithms that exist classically, it's a very simple thing, like it's called nearest centroid, and it says that, imagine you have three types of data, blue, green, and red, right? So when you're fitting your model, what you do is very simple. You compute the average blue point, the average green point, and the average red point, right? So there's these little, circles which are bigger than the others in the middle of your cloud, right? And when a new point comes into your system, this white point over there, what you do is that you try to see how close or how far is this point from the average green, blue, and red point, and you find the closest one. You find the nearest centroid, and you assign the color of that centroid. So here it should be green, right? Because this point is closest to the green average point. So this is the nearest centroid algorithm. It's very basic. It works quite well in many situations. It's not the best that exists out there, but it's also a very important subroutine that we use also for unsupervised learning. For example, the K-means algorithm basically performs a number of nearest centroid classifications as a step within itself, right? Different type of algorithms are kind of quantum neural networks. There you can also define some sort of quantum circuits that play the role of quantum neural networks and try to come up with these quantum algorithms, right? Then what you need to do is kind of go from this quantum algorithm that you write on a paper as a pseudocode to actually doing an experiment on the quantum hardware, right? So to connect these two, you need to write some software, right? And again, here, it's not trivial to take the algorithm and come up with the quantum circuits that implement this algorithm, because there are many different ways of doing it. And as I said, if we didn't care about how many qubits we need or how many gates we're going to apply, then it would be easy because everything is as good as anything else. But given the fact that we have 11 qubits or 50 qubits, but not 10 more, or, you know, or we can do so many operations, but no more, we really need to really make the circuits the smallest possible. Okay, so this is what we do with this quantum software, and then we can send these quantum circuits to a quantum computer, right? It could be the IBM Q machine here. We actually did this experiment with the ion Q machine, which is this trapped ion machine, and we got out some results, right? So the question is, how good were these results? So these results basically say that a quantum machine that exists today, right, can recognize 100 digits 8 out of 10 times, right? So if you give this quantum computer 100 digits, 8 out of 10 times the quantum computer will give you the correct label of the digit. You know, we'll say that the 0 is a 0 or that the 3 is a 3, okay? So this is not the best possible performance that the classical, you know, classifier can have in this type of data set. You can actually get almost 99.3 or 5%, right? But it is not very far from what a classical algorithm can do if you give it the same number of features for this digits, which is 8, because we could only fit 8, you know, features in 8 qubits somehow. Okay. So what I want to say is that I think it's extremely impressive to say that a quantum computer that has 11 qubits, and that's the entire thing of what it has, can actually, you know, classify digits with 80% accuracy, right? But still, we need much more, right? We need better hardware to start becoming competitive with what the classical algorithms can do. Okay. Okay. So I try to be enthusiastic, but also, you know, put things in the right level by saying that I think it's great that you can get 80% accuracy. It will take some time before we can get competitive with classical models, and we need better hardware. We also need to improve the algorithms themselves. Okay.
Iordanis, can I interrupt you with a small question about the hardware here? So this is a trapped ion experiment, and so do you have like what's the connectivity there that you have in your hardware, right? Like, can you apply like 2 qubit gates between distant qubits, or can you? I don't know if you're planning to comment on that.
So this is one of the circuits that we used on the ion Q on the trapped ion machine. The trapped ion machine has the advantage that you have all-to-all connectivity, right? And we took advantage of that in order to create these circuits that can load classical data into quantum states that are extremely shallow, meaning they only have logarithmic depth on the dimension of the data point, of the vector that you're trying to load, right? And the reason that we were able to do that is because, if you can see a little bit in this circuit, there is this tree-like construction. Like, you connect the first and the middle qubits. Let's say these BS gates, it's almost, you know, it's this gate here. It's a reconfigurable beam splitter type gate. But you connect these 2 qubits, then, you know, you have 1 gate in the beginning, 2 gates, then 4 gates, then it will be 8 gates. So there is this tree-like connectivity, which is not exactly embeddable into the grid of IBM or of Google. Okay, we have ways of doing it by doubling the number of qubits, so it's not very far from being embeddable, right? but we can't do it without any overhead on the trapped ion machine because we can't have this exact connectivity that we need. Okay, so yes,
That's great.
in order to find kind of the optimal way of loading the classical data into quantum states, we needed a connectivity which is almost the grid, a little bit better connectivity than the grid, right? It's not going to kill us if we have to use the grid. We can embed it, right? But there will be an overhead. And we use the trapped ions because there is no overhead, right? Because the connectivity was good. Okay. So these are kind of the circuits that enable you to load these data. These are kind of the properties that they have, how many qubits they need, what is the depth of the circuit they need, how many gates they need. And the only reason I put this here is because we can also trade off the number of qubits and the quality of the qubits. So it could be better to use many qubits and very, very shallow circuits because you have many qubits, but they're very noisy. Or you might have fewer qubits, but they're better qubits. And then we can still, squeeze big dimension data points by using fewer qubits and deeper quantum circuits. So you can play with these two kind of properties of your quantum machine, the number of qubits and the quality of the qubits. Okay. Now, once we have these quantum data loaders, we can start estimating distances between points, right? So this is kind of the circuit that we implemented on the trapped ion. So somehow the left part of the circuit is the circuit that loads one of your data points. And the right part of the circuit, which you can see is kind of a mirror image of the first one, basically, is what kind of loads, it's the adjoint circuit of loading the second data point. So if you load these things like that, what you can get at the end of the circuit is an estimate of the inner product or the Euclidean distance of these data points. Okay. So what a quantum computer can do is start estimating the distance between two d-dimensional data points, not in time d, which is what you need in a classical computer, but in log d quantum steps of your quantum circuit. Okay.
And this is good for kernel estimation methods, right? I guess that's where you
exactly. For example, so this is such a basic procedure that you can use it in many different places. We used it in this experiment to estimate the distance between data points and the centroids, right? You can use it to do kernels, right? You can estimate inner products. You can also use it to do matrix vector multiplication, because you multiply matrices with matrices. What you do is inner products, right? You do inner product of a row with an inner product of a column, right? So these are the circuits that can also be used to do matrix, simple linear algebra, right? Not the heavy duty one. For that, the circuits have to be more complicated. But these pretty simple things are things that you can use to do simple linear algebra. Okay. So here is another tool that we have that has to do with neural networks, right? Because to be honest, this is kind of the best techniques that we have for supervised learning, for classification or for regression. The first thing that we try to do is the following. Before trying to define quantum neural networks, the question was, can I use a quantum computer together with a classical neural network in order to speed up the training of this classical neural network? Okay, so I'm still using a classical model, right? But I have on the side, it's kind of a hybrid approach. I have a quantum computer, and the question is, can this quantum computer help me to train the classical model faster, right? And we had some results recently in ICLR where we saw that indeed you can take advantage of, again, the same thing that quantum computers can do, this linear algebra stuff quite fast, to train these classical neural networks faster. Okay. The next, and I think I'm going towards the end of the tools. The next tool, which is it's quite interesting, it has to do with, can we define quantum neural networks, right? So many people have defined quantum neural networks, right? There are many different papers out there where basically what people refer to as a quantum neural network is nothing more than a quantum circuit where the gates have some parameters, right? So for example, you have a rotation gate with an angle theta, right? So you have a bunch of gates in some sort of architecture, right? They have parameters. And then the question is, can I find the correct parameters of the gates so that this circuit will give me a good classification, for example, right? It's not very clear to me why these type of quantum circuits will give you better results than the classical neural networks, for example, right? It's not very clear. And it's not very clear because, even in the classical case, you are not very sure whether a neural network architecture will work or whether you need to use a different one or what is the correct one to use and things like that, right? And we're talking now, it's almost like 30 years or even more that the first classical neural networks, started appearing. And the reason that, we are seeing such a progress when it comes to deep learning is because we have now the hardware to actually test these things and figure out what works and what doesn't work so well, right? So the problem with these quantum neural networks is unfortunately we don't have the hardware to actually test them. We can test very small examples like 8 qubits or 16 qubits or something like that. But if you use 1 qubit per node, usually the neural networks that you use classically have thousands of nodes, right? So you do need much bigger hardware than we have today to start testing quantum neural networks and figuring out what are the good architectures, what works, what doesn't work, what kind of nonlinearities one should use, and so forth. Okay, so what I want to say about quantum neural networks is that it's a very interesting area, right? It has to work in practice. It has to work when we actually use it, right? So I think that these quantum neural networks will be advancing together with the hardware, right? It's the same that Luigi was asking. These are kind of heuristics, right? Neural networks is a heuristic, right? So the heuristic needs to be tested. So the heuristics become better and better also when the hardware becomes better and better. Okay.
Iordanis, we have another question here.
Sure.
So there's Carlos, one of our guys at QRC. The question is the following one. I will read it out. Says, hello, Iordanis. I have a small question. For these examples that you're showing, you are always working within the unitary basis. So at the end, for these particular examples, you have 8 computational basis states for 8 qubits. Cannot it be efficiently simulated classically unless merged with some sort of amplitude estimation? I'm not sure I'm not sure I understand the question very well, but I don't know if you can say something.
Yeah.
I guess he was referring to the previous slide.
Yeah. Even here we have 8 qubits. So if the question is, can I simulate classically what you did with the 8 qubits? The answer is yes. Right? It will take you 2 to the 8 time because there is an exponential, overhead in simulating quantum circuits, right? But not always, depending on the circuit type, right? So indeed, these experiments do not provide an advantage or a supremacy in the sense that we use very few qubits, and these you can simulate classically, right? So up to 30 or 35 qubits, you can always simulate them, okay? The question now is, what can you learn from this, right? So when it comes to this type of algorithms, right, what we know is that we know exactly how this quantum algorithm will scale. We know how to do the same quantum algorithms for 16 or for 1024 qubits or for whatever number of features you have. And we have theoretical proofs of how much time it will take to do these operations, right? And there, when the number of qubits will be increasing, there you will start seeing cases where you cannot simulate this quantum algorithm classically, okay? When it comes to the neural nets, again, you can simulate 8 qubits, right? It's very simple to simulate. This is what I was saying, there is an extra problem with these quantum neural networks, is that it is not very clear if you go from this small neural network that you trained very well and does something good. If you start putting now 1,000 qubits, whether it will train well or what you should be doing, right? Whether you should be adding different architectures, different layers, and all of these things. Okay.
Great,
I
thanks.
hope this was what the question was.
So I see that Carlos is still raising hands, and Andrew, I cannot give permission to speak up to the people. I don't know why. If you're there, Andrew, you could give permission to Carlos. He's raising his hand.
We'll do that.
I'm trying. It would be nice if I could do it myself also. If you can give me permission also for that. But Carlos, do you want to comment on that? Sorry. Let me see if Carlos now can speak.
Now, do you hear me?
Yeah.
Yes, we can hear you. Sorry.
Yeah. Thank you for the answer, Iordanis. Yeah, my question was in particular for this example, because I see that you are working in the unary basis, right? So
for the neural nets.
Yeah, your basis states are gonna be only gonna have one qubit in one, right?
Yeah.
So I can
very good
simulate this efficiently, right, in a classical computer, if I just work on that basis.
Yes.
Which is goes as linear with the number of qubits.
Yeah. So the question is, given that here for the loader or for the neural net, I'm working on the unary basis, in the sense that I'm using a very small part of the Hilbert space with respect to the exponential size Hilbert space.
That's it.
Does this mean that I can simulate this classically efficiently? And the answer is yes, right? So here in the neural networks, I am not trying to say that I can do things faster, right? I'm trying to say that what the quantum thing allows me to do, it allows me to train in a different optimization landscape. Okay, so also the ultimate goal would be to combine this kind of unary loading and stuff with things that will take your space and make it bigger afterwards, right? So the main point with the loaders and stuff was that I don't want to lose my advantage that will come from, for example, the fact that I will be doing some sort of HHL afterwards, or PCA or things like that, because I spend too much time trying to load the data or trying to, so totally, yes, you can simulate in time that depends on the dimension of your Hilbert space, right? But I think there are two things, that this is a part of what you can see as a bigger architecture that at least solves the problem of putting the data in, okay? And second, even though the dimension of the space is the same, okay, and you're not going to a much bigger Hilbert space, the optimization that you're doing and the gradients you are computing in this space is different than what you were doing in the classical case. Okay, which means that maybe you will get different models. Then again, you're right that then maybe I should go back to the classical case again and also do a different type of optimization there. Okay.
Yeah. Okay. Yeah, I see. So at the end, you have to mix this at the end with HHL or amplitude estimation or something like that, right? That's what I mentioned in the question.
Yes.
So in order to have some kind of speed up or say.
Yeah. So these are the last two tools that they become more evolved somehow. So one is the heavier duty linear algebra, right? That has to do with the HHL type algorithm, meaning you can do principal component analysis or this singular value transformations, eigenspace projections, these things which are basically cubic complexity classically, right? This is really where you're going to get some improvement, right?
Okay.
So all of these things that are cubic in the dimension classically, right? The hope is that these quantum algorithms will be much better, right? To do this PCA, for example, and stuff, you still need to load the data, or you still need to use the first part of what I showed you, right? Which will not necessarily give you a speed up on it, but it's not going to kill you the speed up later on because it's as fast, let's say, as the classical one.
Okay, easy. Thank you.
Okay. And the last one, which is also what you said, is that these are also ready to be used with the amplitude estimation, right? And there you will going to get an extra speed up that comes from that. Okay.
Okay.
So this is the last work that we did with some finance institute to say that, you know, we all know how amplitude estimation works, right? It says that you can get a big speed up if you do a very deep kind of quantum circuit, right? So let's say if you are spending 1 over epsilon square samples to simulate something, you can do only 1 over epsilon quantum samples, but you need them to do in sequence, which means that your depth should also be 1 over epsilon. So let's say epsilon is 1 over epsilon is 1,000. What it says is that if you can do a depth 1,000 circuit, then you can do 1,000 times speed up with respect to the classical case, okay? Which is great to get 1,000 times speed up, but it's impossible to do 1,000 depth quantum circuit like anytime soon, right? So what we did here, and you know, the extra point was that we knew that this was optimal. So if you want to get this 1,000 times speed up, you cannot do it with a depth which is less than 1,000. Okay, so that's why, you know, for many people this was kind of the end of the story. This is the speed up that you can get. This is the depth that you need, right? So what we said is a very simple question. What if I sacrifice some of the speed up? Can I use, you know, more shallow circuits, right? And we came up with some sort of, you know, this low depth amplitude estimation algorithm that say that basically it's true. If you need 1,000 times speed up, you need 1,000 depth quantum circuit. But if you need 100 times speed up, you need 100 depth circuit. And if you need 10 times speed up, you can do it with 10 depth circuit, right? So a 10 times speed up, it's actually really important, right? 1,000, it's amazing. But even being able to do things 10 times faster means that something that takes overnight to be done, right? You need 10 hours to do it, you can do it in an hour, and you can do it on the same day, right? And the quantum circuits, or the quality of qubits that you will need to do something like that, it's much, much lower than what you would need to do a 1,000 depth quantum circuit, because you only need to do a 10 depth quantum circuit. Okay. Okay, so I think I'm gonna go very quickly through the slide just so that I showed you they're just other applications, but if you know the tools, and I wanted you, you know, to see what are the tools that we use, then it's pretty simple to see what the applications can happen, right? So recommendation systems was one of the first ones that we came up with, because it has to do, again, with singular values and eigenvalues and eigenvectors, and this is something a quantum computer can do faster than a classical computer. There was a big, you know, discussion about whether it's an exponential or a polynomial speedup. In the end, it's a polynomial speedup with respect to the classical one. But in practice, you know, we're still much better on the steps than the classical case, and also these quantum-inspired classical techniques. Actually, the previous classical methods are much better in practice than these quantum-inspired techniques. But still, the quantum is better than both of them theoretically when you look at the theorems and some parameters that that we have in practice, like for the Amazon matrix and things like that. You can do clustering. As I said, this nearest centroids is one of the basic steps of this clustering. So this is a little more complicated algorithm, and you need a little bit more complicated linear algebra, but it's still possible to do. More complicated clustering, like expectation maximization, spectral clustering. Again, you look at all these things, there is a lot of linear algebra at the core of these things. You can use these techniques that we have for linear algebra to say something interesting about quantum algorithms. It's not as easy. It doesn't work always. So it's not a plug and play kind of thing. This is the theorem, I put it there and it works. These things are quite subtle to work out, but it's not impossible, right? And the last one has to do with reinforcement learning. This is quite new. The paper is still not out. It should be in a couple of weeks. This is a very interesting area of machine learning, you know, with all this AlphaGo and the DeepMind and all this kind of, you know, very fancy stuff. The good news about quantum is that this part of machine learning has some advantages which are kind of good for quantum circuits and quantum machine learning. For example, there's not big data, right? We don't have high definition, millions of images that we want to load, right? This is something where you learn and you create the data as you play the game, little by little, right? Also, this kind of linear algebra there is kind of nice for quantum algorithms because the matrices are positive, they're well conditioned, there are all these kind of subtleties there, which are kind of on a good side on this reinforcement learning path, which may not be the case for solving linear systems in general, for example, right? Because you have to take care of many, many different things. So I'm going to skip the optimization and I'm just going to conclude because I want to also leave a few minutes for any more questions. So I wanted to say that we have some very powerful tools, right? But they're extremely subtle. So these quantum tools can be used for many things that are relevant to machine learning, for linear algebra, for distance estimation, for computing expectations and things like that. But there are many subtleties on how do you deal with the classical input? What do you do with the quantum input? Because what you get out of these procedures is a quantum state. Does this quantum state have the information that you need and how do you extract it, for example? The running time parameters of these quantum procedures have 10 parameters in it. So you really need to understand if these parameters are good or bad, and this depends on the use case. It even depends on the specific data sets, right? So these are not, at this point, these are not kind of black box and off-the-shelf algorithms where they will all work no matter what your data set is, right? So it's case by case. You need to understand these parameters, and there are variants of these quantum algorithms that work better for this parameter region and not for that parameter region, right? But there are some very promising directions, things that have to do with these heavy linear algebra techniques, like this dimensionality reduction, support vector machines, anything which is this cubic thing classically. This is what we hope to do, and some of the cases we are actually done it, is to do some sort of linear dependence instead of cubic dependence for the quantum algorithm, right? And this is the real quantum running time and stuff, right? The last thing I want to say is that I think there are many more applications that will be happening, right? We just need to try and we just need to look for them, right? And there is a lot of work still to be done, but you know, as long as there is no fundamental reason why this is not going to work, I still believe that it is going to work, right? And so far there is no fundamental reason why it shouldn't work. And I think it's more than enough of an incentive to actually try and make these NISQ machines useful for something. I mean, we're spending billions on trying to build them, not me, but all, you know, there's so many public money spent on this and private money. And I think we need to really, really understand how useful they are. And for that, we need to work, as Leandro was saying, with computer scientists, with physicists, with experimentalists. We have to understand, you know, what these machines look like and what kind of noise they have, and how can I make my algorithm to be okay with this type of noise, right? So we need to make our hands a bit dirty, right? But there is a lot of things to be done. And yeah, and I think we all gonna make a really great impact in the future. So thanks a lot. And that's all I had.
Thank you so much, Iordanis. Thank you for the fantastic talk. This has been really nice. You drove us smoothly into an overview of so many different things you guys have been doing. I have, let's see if somebody has some questions, but before they warm up with the questions, I myself have a, like, so there's this part in one of your last slides where you mentioned the optimality results in the sense of, like, if you want to speed up of 10 times, then you need at least to have a circuit depth of 10 times deeper, or if you want to speed up 100 times. So can you comment of what type, what is it like no-go results for the depth, if you want to,
Yes.
But is it in this paper that you're showing here, or okay?
So the no-go results before was only looking at the full amplitude estimation, and saying that if you want to get the full possible speed up, which is this 1 over epsilon
quadratic factor, you mean like a quadratic speed up?
Exactly. Yeah. If you want to get the quadratic speed up, then you need to have the circuits which are this deep.
Right.
Okay? What we proved is kind of, again, it's like a trade-off between the speed up and the depth of your circuits, right? So we showed that for whatever depth you have, right? If you give me a quantum machine that can go up to this depth, okay, then I can tell you what is the optimal speed up that you can get with that depth, okay? And the good news is that the speed up doesn't start after a depth 1000, it starts immediately, right? And it grows as the depth grows, the speed up also grows all the way to the full speed up, the full quadratic speed up, when your depth is also 1/epsilon.
I see. So you've provided now a complete spectrum of speedups between nothing and the full quadratic case. I see. Yeah. That's very nice. Very interesting. Thanks. And then something else that I would like to hear more is in the beginning where you were showing these circuits for loading classical data into your classification schemes, right? So I guess that's like a feature, like a sort of quantum feature map, some people call it, right? So you didn't mention many details of that, right? You just showed the circuit. Can you convey some intuition of why you chose that circuit with that particular structure, or if you could comment a little bit on that?
Yeah. So the one I showed you, which is what we call the parallel loader, which has the most number of qubits and the shallowest possible circuit depth, is using this unary representation of the data.
Right.
Meaning that if you have d dimensions, right, we use d qubits.
Yeah.
And by looking at the basis states that have all zeros and 1 1 in different places, which are d of them, we put the amplitude that corresponds to your classical vector as an amplitude in this superposition, okay, of d different computational bases. When we trade off the qubits with the depth, then this is not a unary representation anymore. Okay. The reason we did this is because of how the hardware is advancing, meaning that for now it's easier to have 100 noisy qubits than 20 extremely good qubits that you can keep for very long.
True.
Right? So this is why we use this encoding. There are different encodings, right? As I said, you can play a bit with the number of qubits and stuff. It is also kind of natural when you look at the neural networks where you use one node per feature, meaning that when you have data points with d features, you have d nodes, one node per feature. So it's the same number of qubits that we use for the loader is the same number of qubits that we have for the neural network. So you can put the loader in front of the neural network and it's the same number of qubits between them.
Right. Okay, cool. Thank you. So I see some people raising hands. Okay, a couple more minutes. So I see Luigi and Carlos are raising hands, but I don't know if this was from today or Luigi, Carlos, do you want to add something?
No, I raised the hands.
Yeah, go ahead.
Okay.
Yeah.
So I have a very general question, and please, Iordanis, forgive me if I say something wrong. Say when you basically construct the neural networks, compared with within classical or the standard analysis, basically you make a transition between the kind of linear computation to non-linear one, right? Basically, the same thing. Say you guys want to do with the quantum neural network. So you go from a quantum computer, which is based on a linear programming, to a quantum to a non-linear, say, information processing. But I think in the quantum case, I think it's might be a little bit. Say, first of all, the first question is if it is known what kind of, at least theoretically, the kind of speed up or the kind of outperforming that you have from going from quantum computer ordinary to quantum neural networks. This is the first part of the question. And then I think I see that say, playing with these quantum neural networks, you play with the very subtle things indeed, because you play with quantum mechanics together with nonlinear things. And I think the interplay between the two things, it's very interesting and challenging. And I think, say, the second part of the question is whether anything is really known on the interplay between quantum mechanics and nonlinear phenomena.
Yeah,
Good.
yeah. Okay,
Question.
very good question. So, so I guess the question is, one of the main reasons why classical neural networks work is because of this nonlinear element, right? If you remove this nonlinearity at the end of every layer, then these things don't work, right? So we cannot remove this nonlinearity, right? Now, as you say very well, a quantum circuit is a unitary circuit, so there is no nonlinearity in this thing, right? So how do we deal with this? So there are a couple of different proposals out there. One proposal is to say that, as you continue your quantum circuit, what you can do is kind of measure some of your qubits and then continue with the rest of the qubits. Okay, so this adds a nonlinear element, which is the measurement, right? So the nonlinear element of the quantum, world somehow is what happens when you measure. Okay. So one option is to say that, I start with 100 qubits, and once I do this unitary circuit, I kind of disregard what happens to 50 of them, and I continue with the other 50. So if you see the map between the 100 to the 50, this is a general map, which is a nonlinear map.
True.
There is another way of doing it, which is to say that I'm going to look at each layer separately of the neural network as a quantum circuit, right? And then what you do is that at the end, again, you measure, you get a classical result. And on the classical result, you can apply classically the nonlinearity, like a sigmoid or a ReLU function or something like that, right? And then on that becomes the input to your next quantum layer, right? Which is now, so either you can go back between the classical and quantum by saying, I apply a quantum thing, I measure to get a classical result, I apply a nonlinearity, I load it to my next quantum layer, I do a quantum layer and so forth. So it's kind of a more hybrid type of thing. Or you can use tricks like using more qubits and getting rid of qubits to somehow add this nonlinearity element. But you're very right, it's not clear why it is better or why it is worse, or what is obvious that we will gain by using quantum neural networks, right? Like, I don't believe necessarily this argument that, oh, but your Hilbert space is exponentially larger, so you will explore much more. Sure. It's also much more difficult to find, something that you want if you have an exponentially larger place that you will get lost, right? So we have to be very careful about how we deal with these things. And that's why I say it's a very interesting area, but somehow the jury is still out there on how much you can gain by these quantum neural networks.
Excellent.
Thank you.
Yeah. Carlos, do you have another comment there, or?
No, I simply forgot to unraise the hand.
Okay, no problem.
Great.
Iordanis, I have a couple more questions here, simple ones in the Q&A icon. Okay.
Sure.
So there's Stefano Carrazza. He's from the quantum middleware group in our center. So the question is the following: Dear Iordanis, thank you very much for the great presentation. What is your opinion about generative models? Thank you. Like on quantum generative models, I guess. Yeah.
Also very interesting. There is one good thing about generative models, which is it kind of plays to the strength of quantum, which is that, given that the output of these quantum things is a superposition of states, one simple thing that you can do is sample. Right?
It's a sampling machine.
Exactly. Yeah. So using it for a sampling task is kind of more intuitive than using it for a decision thing where you need to say 0 or 1 somehow, right? Again, is it clear that using quantum circuits to generate distributions will work better than classical ones? not clear. But one case where it is necessary to use, quantum generative models is when you want to express quantum distributions, right? So this is a case where you cannot do it classically. So then you do have to do some sort of quantum generative models or even GANs or things like that. And yeah, maybe, it's even simpler to make this work than making work like a classification task on a neural network. So yeah, why not?
And we have another last question here, more on the commercial application side. This is Renato Melo from our group also, and the question is the following: given the current pace in development of bigger and bigger quantum hardware and noise control, how long do you think it will take to get to useful business applications? Right, that's the question everybody wants to answer.
Yeah, that's the $1 billion question. I agree.
So your bet,
So okay, all I can say is that if you had asked me 10 years ago, I would say never. If you had asked me 5 years ago, I would say possibly at some point. If you ask me now, I would say, 5 to 10 years. Why not? So all I'm saying is that there are two things, as I said in the beginning, that should happen, right? The hardware should become better, right? But the point is that we're not just waiting for the hardware to become better. It's not like we fix the algorithm that needs 1 million qubits and we're just waiting for the hardware to reach the 1 million qubits, right? If this is the case, then we're going to wait a long time, right? The question is, can we also move from the other side and go from something that needs 1 million qubits to something that needs 1,000 qubits? Because then we shaved off 10 years from the hardware development, right? So this is exactly why I think that it's moving faster than we think. It's also because of the algorithmic development of bringing down these resources of what we need. Okay, so so don't quote me on a number, but from what I have seen in the last 5 years, I think it's getting closer, right? So the predictions are getting more bold on the number of years.
Right. Yeah, it's really exciting to hear all these developments.